much confidence that it's there. So how could you do that? Well, you could do that by making a reference model that didn't have this. So take the solution that you already have. It basically fits the data. Get rid of the picture that you're querying. And then make a reference model that is representative of the model without the feature. Assign a high weighting, WS, to this part to try to force it close to this reference and then see what happens. So we did that in this case, and the result was something that looked like this. Basically, this high conductivity feature more or less went away. So it's not surprising really that it did, because it's kind of on the outside of the data array, but it basically really diminished. So you just wouldn't have a lot of confidence that that's there. So that's one way of kind of doing. We call it hypothesis testing, and we've used that a number of times to kind of help clarify whether something is really demanded by the data or not. Something else that's actually been very useful for us is in particular surveys to try to characterize just how deeply you're seeing with a particular survey. And again, we've got tools to do that, because we had our model objective function look like smallness plus a vertical parameter, and our smallness is given by this. So what we want to do is carry out two inversions, but that have different reference models. So the idea is kind of the following. Like here's a 1D Earth model, and if I use a reference model of 30 ohm meters, I get the blue line. If I use a reference model of 50 ohm meters, I get the red. So why is that important? What you notice is that down deep here, all you're getting back is whatever the reference model was, irrespective of the implementation. So actually, you have no confidence that that is really demanded by the data. Whereas up here, even though you change the value of the reference model, you don't change the solution. So you get the sense that, okay, this is really intrinsically connected, it's demanded by the data, and then there's a bit of a transition zone. So one can quantify this by doing what we call a depth of investigation index, looking at the difference between the two models divided by the difference in the reference models. And when we do that for this 1D case, the depth of investigation index, so in one means that it's just entirely controlled by the reference. Someplace up in here, starting to see that, okay, that's about as deep as the data are seeing. So you can actually truncate your inversions off at that point. I might also say that when you're conveying physical information to other people who do not know how the inversion procedure was carried out or details of this, if you show them a picture that has got artifacts on the outside that aren't really representative of what the data are, it can really torque your conversation off into left field, because they might focus on that, and then you say, oh, well, really we don't have the resolution to see that, so don't look at that. Can't do that. So you need to cut things off before you show it to anybody else. And this is sort of one technique that can help sometimes. Just do it. Now you're running two inversions, which you probably want to do anyway, and see what the difference is and use the differences in that. The other thing that is very usefully employed is to do parametric representations of what you're looking for. So the thing is sometimes in order to solve the forward problem, you need to have 100,000 or a million cells to be working with. But when you do the inverse problem, there's lots of places where you just don't have the sensitivity of the data to really refine or get that kind of resolution out. And sometimes it's simply not the answer that you're looking for, right? Because if you think about geology, for instance, then maybe just representing the Earth in terms of a sphere, ellipsoid, or plate is actually perfectly fine. It captures the information that you really want to convey. That's enough. And then you're down to just hitting a few parameters, the location of the sphere, conductivity, radius, conductivity background. So you really change the nature of that problem. Here's an example, for instance, in fracking, which is of interest. Here you've got sort of a well, you're going to be fracking along here. You really don't need to have cells that are, a half a meter, resolution along here. And also, you certainly don't need to have anything, that is, high resolution. You just don't need those cells in your version. You don't have enough information to control that result anyway. So maybe you're better off to say, okay, for the inversion part, I'm just going to try to find, few plates here and their orientation and characteristics. That greatly changes the inverse problem. Now you really don't have so much as an inverse problem as just a parameter estimation problem. So you actually can have an overdetermined problem since you've got more data than you have unknowns. You can still formulate everything exactly as you've done, except the term that we've been spending almost all of the day on, this model objective function, just goes up into it. It could be just so now, perhaps we really are thinking about just misfit. There are, of course, times when you kind of want to transition, but that's really basic bifurcation that in what we did this morning, the model objective function played a really huge role. When we come down to parameter estimation, we don't even need that, and we're just looking at misfits. So all of the techniques that we use, gradient methods, the Gauss-Newton, it can still be used here, but the outcome can be very sensitive to what the starting values are, so you need to be cognizant of that. Here's an example. Here is a time domain EM system that's flying over a plate, and the response is given by this. And one can choose to invert this using different representations. For instance, if you invert this assuming a 1D Earth, you get something that looks like this. You get the top of the body, and then you kind of get these wings on the side. So very strong artifacts because you don't have the right dimensionality. If you do a 2D inversion, the result is something like this. So it's pretty good. You've got something that's localized, going deeper. But if you do a parametric inversion, where you're just looking for a plate, then you end up with something that looks like this. So you don't get the full extent of the plate because you're dealing with a sensitivity. So here's an example. This is a particular case. Parametric has done a pretty reasonable job at doing things, and you're only looking for a few parameters. Whereas here you've got different degrees of success. The one thing I wanted to perhaps mention here, and talk a bit about Wednesday, is that these results are all generated with our open source modules, SimPay. So this is a package that we put together for doing scientific computing, and in particular, the forward and the inverse problem. What's nice about this is that it's an object-oriented package. It uses Python. And everything is kind of hooked up so that if you want to change from a 1D inversion to a 2D inversion to a parametric inversion, really there's only a couple of links and modules that you need to incorporate, just how you're defining the forward modeling and the inversion parameters, and then you can go ahead and do it. That's a huge power, I think, about object-oriented programming and generation of a package that allows you to link up a whole bunch of different modules and solve different kinds of problems. It greatly accelerates the research that can be done. The other way of reducing uncertainty is having multiple surveys that are connected with the same physical property. We've seen this a number of times. Here's a time domain system up here. Here's a frequency domain system. Here's a ground system. And in spite of the fact that individually we might be able to invert each of these, sometimes when we found this, see that the way programs could invert, say, the resolve data, and the programs that could invert the GeoTem data and the ground data, but we didn't have anything to kind of put them all together. So here again, this modular package of SimPay allowed us to jointly invert all of these three different data sets, much less. So in setting up the inversion, you have these different systems. The important part here is this frequency domain system is high frequency and doesn't have a very large depth of investigation, maybe 70 meters. The ground nanochem time domain system might see a little bit deeper to 300, and the GeoTem system sort of sees down pressed to 300 meters. If you take each of the data sets individually and invert them, you get something like this. So the true model looks like this. It's conductive near surface region and then a resistive region beneath. If you do the resolve the frequency domain system, you get something kind of a bit of a bump that goes there. But remember I said that depth of investigation is only maybe 70 meters. So that's really all you see. The GeoTem system has got deep penetration, but it doesn't have high resolution at shallow depth, so the inversion of that, like that. And then the nanochem, that was the one on the ground, ended up having something that looked like this. So again, it didn't see deep. So this is something that can help reduce uncertainty just by having different systems that sense the Earth differently. And if we took those and inverted everything all at once, we end up with a joint inversion now that looks like this. So this has actually done a pretty nice job of finding this guy as well as this, and then going back to the background. So this is all done with L2 inversions. If we now take that same thing and go with an L0 norm that I talked about, then this is the result you get. So the result comes out like this. GeoTem, nanochem, and then the joint. So this is actually a pretty nice representation. We've got just a few elements here that are different backgrounds. So this layer here, and this layer here. And compared to what we had before, certainly that's a superior result. This is because it's more, you've got more of that right character that's associated with what the true model is. So I think the take-home message there is that taking more data that are sensitive to the same physical property and choosing the right kind of norm for the problem and inverting the join day, you're going to do that. So what happens if we have multiple physical properties? So this is kind of what we had at TAC. I think the first question is, in general, okay, what do you want to extract? What's your mission? What do you really want to get out from all of these data? You know, is it just kind of the shape of this kimberlite pipe, or is it delineation of these various units, or what's your question? And your question might change as the exploration program is going on. This part might be like, okay, find me a pipe. And the next question might be more detailed. So your question might change. If you got multiple physical properties, then there's a question of like, okay, what do I do with those? I mean, how are they connected? And that's the big thing with joint inversion. It's like, how do you connect? Now, in psychology, you sometimes have a relationship between the seismic velocity and the density. So if that was the case, you could put that kind of law connection in, then you could easily imagine a joint inversion. The other thing that's been popular over the last decade is joint inversion for structure. And what you mean by that is that I don't know if, how the electrical resistivity and the susceptibility are going to change between the rock units. I just know that they're going to be different. So if there's a fault separating two rock units, I might know that I expect a change in the susceptibility on both sides, a change in the electrical conductivity on both sides. I just don't know whether they're going to go up or down or whatever. But I'm looking for changes to occur at the same place. So that's another one. The other way that has some potential is gaining some insight by doing like a posterior analysis of the inversion modules or the inversion results that I already have, for instance, at TPC. I should show you what I mean by that. So we have this kimberlite pipe, it's got different rocks, and if we look at the different rock units, we've got density, susceptibility, conductivity, and something called chargeability is related to IP. But we see that each rock unit has got sort of a different amount of information. So this HK unit is low on density, high on susceptibility, moderate conductivity, whereas the BK unit, low density, low to moderate susceptibility, and moderately high conductivity. So the rock units got different kind of characteristics or combinations of these physical properties. So one could imagine a classification whereby you choose a rock unit 1 that's got high density, low susceptibility, high conductivity, and low chargeability. Right? So you could imagine various combinations of these things giving rise to what you could call a geophysical rock unit. So we could do that by looking at our various data sets. So we put for the EM data at DKC, we had a number of different airborne EM systems that we combined and computed the conductivity of. So I showed you this a little bit before. We have a conductivity model over the air. So that's one piece of information. We also have potential fields. So we've got magnetic radiometer data, and we've got gravity radiometer data, and we've got magnetic data. So those are two other data sets from which we can get information. So the gravity radiometer gives a 3D model of density that looks like this, horizontal view, really low density here, and cross sections like that. The kimberlite pipes are generally low. And then the magnetic data gives rise to magnetic susceptibility that looks like this. And there's something called chargeability. It's basically the IP model that early times, late times. Anyway, that's another kind of think about it as a physical property, and there's a late time. So the bottom line is that there's 5, like we got 5 volumes, okay? And now we do a classification of each pixel to decide, okay, whether it's got high this, low this, high that, and we make these different rock units. So rock unit 1, for instance, has got low density, low susceptibility, low conductivity, low chargeability, early and late. So that's rock unit 1. Rock unit 4 is low density, moderate susceptibility, moderate conductivity, high early time, chargeability low. So that's another classification, and those are related to particular kinds of kimberlite rock. So here's, you kind of put all that together. So you can imagine the amount of work here. I was very impressed with the group at UBC that was extraordinarily intelligent, and this was probably close to a 2-year project by the time we started when we finished. But at the end of the day, we had 5 volumes of basically different physical properties. And then now we're going to do a post-inversion classification. And this is what happens. So we got, here's the rock units, 0 to 5. So the green is rock 5, the red is rock 4. And so you can kind of see how they match. And then we were fortunate enough in this case that they had a lot of drills, because this was actually, and still is, potentially a productive diamond mine. They had a lot of drills, so we then had geologic information about what these units were. And the red here is indicating the BK unit, the kind of yellow here is the HK, and the green is the PK. And you can see how there's this correspondence between those two images. So that's really nice. That was really satisfying that we could take these data, and actually these are all airborne data. So they're flown fairly readily over the area. So the gravity, the magnetics, and the electric conductivity. You could take those data, invert them, and not find location flight, but maybe something really interesting about the geology that would certainly help them pinpoint where they're going to do, let's say, a first drill. I guess the last thing I want to talk about in this section is some of the latest work that we've been doing, and this is the credit for this goes to Thibaut Assig, and it's going to kind of combine some stuff that we're traditionally doing with what Bayesian group, Nicholas and JC are going to do. And the question here is, what about other data? What about petrophysical data, right? And how do you put that stuff in? So in one of the areas, here's the on-site, lab, some drill cores. Here's physical property measurements. So here's how you do DC facility experiment. And what we're looking at here is resistivity as a function of chargeability. And you can see there's clusters, right? So there's kind of organized down here, and there's some greens here and some blues here. There's stuff that's scattered around, but you kind of get the idea that maybe these things are clustered, and you put them on a plot, you can actually see some trends that are there. So I want to show you, first of all, I want to show you how synthetic for where we think we're going to go. How we're going to do it. So here's a pipe. Here's the gravity table, and here's the kinetic table. Okay. Now what we did this morning, I do an L2 inversion. So I do an L2 inversion, yeah, I get this, right? So, I got something in the right place, and kind of in depth, magnetics, I don't know, there's something really kind of blurry here. So it's not really high definition, kind of tells you there's something there, but not quite what you want. What we should do, what we're really interested in doing is getting, if we look at this PK unit, well, this is density and this is magnetic susceptibility. And the values kind of plot in here. So this particular rock has that combination of density and susceptibility that are associated. The HK unit over here has a really high magnetic susceptibility and a lower density. So it's plotting up in here. And the background is kind of sitting up here, pretty close to zero. So that's really raw information that we somehow like to include in the inversions. So one of the things that you can think about is, like, if you're trying to think about a probability density function for this, and you're going to hear a lot about this in the next couple of days, but here's just like a Gaussian probability that could be associated with these, and here's another Gaussian for that, and you could have a Gaussian for that. If we look at what happened with the true, our initial inversions with the L2, so the susceptibility and the density, and we took those models and we plotted them up, okay, to look to see where they plot on this joint density and susceptibility. See, most of them are kind of down here. There's just a couple that sort of get here, but there's no concentration of points here, and there's no concentration of points there. So that means that these models, which independently fit their data, they're not really compatible with the petrophysical data. We're not getting out the kind of solution that we'd really like. We'd like to get something out that's got a concentration of values here, concentration of values here, and maybe something. That's what we'd really like. So how do we do that? Well, we've got geophysics, we've got petrophysics, and we want to somehow combine them with the geology. These things are all really linked. And what it means is that for each pixel in our model, we need to have a physical property that's associated with like a viable rock unit. And then we also need to have a geologic identifier that tells us which rock unit that is. So globally, both the physical data and the petrophysical data need to fit. And we need to make everything consistent into a framework that is manageable. So here is what is proposed. We've got geophysical data, petrophysical data, and geological data. To divide this up into 3 inversions. So here's the physical version. Here's the petrophysical characterization. I'll talk about that in a second. And here's the geologic identification. And these things all connect with each other. And they're going to be done in sort of an iterative fashion. So let's just take the first one, the geophysical inversion. We know about that. So we take physical data, we take all our prior information, which is basically the reference model and the weights associated with the smallest objective function. So that's our prior function. We put that in. We're going to minimize this guy here, where we've got smallest bulk component and a big component. And then we solve that, and we update them all in. Okay, this guy here. The next thing is a petrophysical characterization. How do we represent the petrophysical model? Well, we're going to do it with what's called a Gaussian mixture model. So for each rock unit that we've got, it's going to be represented by a Gaussian distribution, and we will it'll have a certain mean value, and it will have a certain variance or standard deviation. So that's kind of what we think about for different rock units. Like, okay, it's sort of values are kind of standard. It's got a mean, and it's got a kind of standard deviation. And then we're going to say that our final GMM is going to be a sum of all of these. It's a generalized Gaussian mixture. Okay. So now we're going to solve this problem. And the input of that, first of all, is the physical data. So in this here, the physical data gives us the probability and the property. So it's got like sort of like two Gaussians. So this one. Okay, that's good. Then we have the prior input from our general maximum. Pi here is the proportionality of each rock unit. Mu is the mean, and sigma is the standard deviation. So in this case here, there's 2, and pi, the proportionality might be like 0.3, and the proportionality is like 0.7, so that if you take up a rock, then there's a 70% chance it's rock 2. The prior distribution is this dashed line here, and then put into this, this inversion, which is a map EM solution, you end up with something now that looks like the solid curve here. So that readjusts what your Gaussian mixture model is, and it outputs the new proportionality, the new set of means, and standard deviations. The third one is the geologic identification. So in this case, the input is your Gaussian mixture model, and also your prior information, in this case, is your geophysical model. And basically what you're trying to do, you've got a GMM is the solid line. And then for each model element that you've got, so you take a pixel, you look at what the property is, and you find out, oh, it's like -3, so I'm going to assign that to rock unit. Or if you had the value of 4, you assign it to a rock unit 2. So that allows us to take each pixel in our volume and assign it a particular rock type. So here's what happens. So if we look at the inversion of magnetic physics, so here's the gravity, here's the magnetics. Here was our generalized GMM that arises from that. And you look at the classification, and you just find like, oh, I can't tell anything. It's just a blob. Everything is just too blurred out. So now we're going to carry our inversion using our GMM and look to see what happens. And when we do that, then we join gravity inversion and magnetic inversion now looks like this, and the geologic description is looking like this. So here, the black is the HK unit, and the orange is the PK, and so we've clearly got two different kinds of rock units. And if you look at the joint probability, then you see there's three clusters. There's one here for the background, there's one here for the PK, and there's one for the HK. So that's doing the kind of thing that we hope. We not only have density and magnetic susceptibility distributions that fit the geophysical data, but if you look at their values, their probability density functions lie on something that seems pretty reasonable, and we divided these things into particular rock units. So that, I think, is kind of where we're going. This is pretty recent stuff from our perspective. Thibault has just submitted a first paper on that, but I think it holds a lot of promise. And the other thing that we're kind of going to is not only is petrophysically guided inversion, but also incorporating that with the L0, L1 norms, right? So the combination of those two things, I think, are going to make a good step forward in getting good information. So that was kind of what I wanted to say for this. We kind of looked at large-scale conversions, and we sort of attempted to address uncertainty through a variety of mechanisms. So the last thing I want to do is just basically take a minute, wrap up, and just talk a little bit about the future. Hello. My computer's getting as slow as the other guy. So we haven't uploaded all the slides, but that will happen. But everything that we've done, all the slides will be available, as well as, I guess this is all live streamed, right? So all that's, yeah.
We'll share the recording as well.
So in our efforts to record as many things as possible. Here we go. So you've seen this. Here's our flow. This is where we started this morning. We wanted to do an overview, T-graph, SVD, linear, nonlinear, LP norms, field scale, and the future. I just want to run through like one slide for each of these, just to kind of remember where we were. So that first part, our overview, we're just really trying to set the scene about mapping, jargon, non-uniqueness, and we concluded that the inverse problem is ill-posed. That meant that we needed to add information. So we've got a box like this, and we've got these various types of information, and we want to somehow put that in. Throughout the course, we've been gradually putting more and more of that information in. On the Tikhonov, we've set up the problem so that we have a misfit, model check function, we're going to minimize this, where beta is our regularization parameter. And we provided an app that you can go ahead and play with. SVD, We take the matrix that we're interested in, our forward modeling matrix for a linear problem, and we decompose that into product of three matrices. The matrix E, it's columns, vectors in the activated model space. U are the activated data vectors in data space, and lambda for the singular positive number. And the thing about this is that it connects each vector VI connects with UI, vice versa. Under the strategic trust. So that means there's an infinite connection. But we don't necessarily want to use all these of those. We just maybe want to use a few. And there's a lot of those cause just more harm than good. So we find a kind of solution kind of lies in the subspace. And actually by truncating like this, it's just the same as treating both the nucleus and the conditioning at one go. And then we show that as you truncate you kind of sliding down on that Tikhonov curve. By the time you get to 5 or 6 vectors, you've actually squeezed about as much as you can out of those data. So what that solution tells us is that the full data set can tell us something about all of the parallel, but really there's only a portion of even that space that is really useful for us. Then we went to the linear inverse problem. So we've got a misfit, all norm, quantity here. The thing about that is we've got a quadratic objective function, so we can get to the minimum in one step. So that's good. The only thing was we need to choose the beta value. And you could set the way we did here, you could set a range of betas. And then you could go ahead and explore to see how the model is behaving as beta is changing. And then we try to pick up something that was either close to an expected value in this fit, or in more general terms, very often you want to plot out the full Tikhonov curve and try to find something in this area, but on the upside. In the 2D tomography, we had situation like this, where this was recovered, and kind of got something in about the right place, kind of lower amplitude. We showed that we could put in more a priori information by having weights in here and being very judicious about where we want to make that weight large or small. So the reference model and the weights were pretty useful. Introduced sensitivity weighting. We actually use this in a lot of different codes, especially when you're data deficient. With sensitivity weighting, the 3D magnetic model recovered kind of looks like that. Without sensitivity, everything just rises to the top because that's where your sensitivities are. By the way, other places that it's very useful to have sensitivity weighting is right around any receiver, you're clearly going to be very sensitive to what is happening. So if you just go ahead and invert, and you'll very often see a choppy, checkerboard type of structure that's coinciding with where the receivers are. And so some kind of sensitivity way to get rid of that would be extremely useful. In the nonlinear, we made use of what we did with the L2 by always looking for just kind of local quadratic functions, and then minimize this. So we showed the complete correspondence between what we did with linear versus nonlinear, except that the nonlinear we're just going to do this multiple times and iterate its successive delta x's. And then for the general algorithm, we just go ahead and iteratively solve that, introduce a cooling mechanism that works pretty nicely for most of our problems, and we end up solving a system equations like that. So that's J. And now we're going to do J is a big matrix and it's full and it stands, right? So sometimes we don't, we just can't compute or store that. So we're going back to J and use it. So in general PDE-based equations, you're going to have to set up a grid, a finite volume, a linear system that we could work with, and then generically have something that looks like this, and then we're going to solve that. The sensitivity, as I was just saying, is really properly set up by having it as a product of three matrices. So one is this kind of generalized matrix that you've got. Here's our forward modeling matrix that's got an inverse that solves the forward modeling problem, and P is a projection matrix. So by factoring that, by having nodes, you can actually go a long way in working with big problems. So putting everything together, we end up with a system like this, and the way in which we solved it, which I didn't elaborate on, was that we have to do an iterative multiplication of the left-hand side matrix onto whatever's on the right-hand side, which meant J transpose times the vector J times vector. DC resistivity inversions, we showed something like this. Here's the true model observed, and here's our final predictive model. And then we had a field example where we went ahead and inverted field data and got a conductivity model that looks something like that. Then the LP norms, that's just what we did this afternoon. So we got 1D, 2D, or 3D. These were our generic conversions. And we saw L2 just kind of generally smooth bounded as artifacts of physics. So we introduced the general LP norm. That's the sum of these, whatever quantity, either the model or its derivative raised to a particular power. P is between 0 and 2. And for the cross-bell, we ended up with something that looks like this. So this is very much closer to the kind of character of what we've really got compared to smooth boundaries. And we had an example with Pizza, which did multiple inversions of different combinations of those p-values. And we ended up with stuff that was very geologically oriented. So here's the contours for geology, and here's the high. And that was much more explicable with the seismic controls. For the field scale, I think the big takeaway message is that there's, even with a big problem, basically the things that we've done for our nonlinear problems are completely applicable. So we go through the flowchart. It's fine. The thing that really makes it work are these advances in scientific computing, and in particular the separation of local and global meshes, access to multi-cores, and handling sensitivity. Put them all together and solve big problems. And then for inverting with quantum physics, we had joint inversions. Then we had multiple properties that we put together. And then lastly, we just finished up with this physically guided version. So let's kind of wind up here by trying to kind of summarize like where we are. And I think we now have a very good basic understanding about the inverse problem. So the next is the applications of large-scale, multidisciplinary problems. And that is, I think, is where we are as the geophysics community at this point, trying to figure out, okay, where can we really make a difference? I showed you some applications early on, whether it was minerals, contaminants, or geothermal energy, technical, whatever. These are problems that geophysics has the potential for really making an impact on. The question is, how do we do that? What role does geophysics play? How do we integrate that? I think this is kind of interesting kind of image and question. So this is that Edmonton Calgary corridor I talked about. So it's a large scale problem, and you've flown all of this airborne EM over it, and you can convert it to get electrical conductivity. But really, it's a question of like, okay, is that the end product? Is that what you really want? Because conductivity itself doesn't really translate to geology, and it doesn't translate to hydrogeology. So it plays a role, but it isn't a complete answer. So then, okay, so what are the questions? And I think this, from the point of view of a practicing geophysicist, is one of the most important things that we can wrap our heads around, and that is, okay, what are the questions that you really want to ask? So they might be, where are the aquifers, the aquifers? What's the water quality? Have arsenic in it? Salt water? What's the storage capacity, flow rate? How are the aquifers recharged or not? And are the aquifers losing or gaining water? Sort of a water balance issue. And the other thing is like, okay, who are we dealing with? Who's the stakeholders? Clearly the farmers are a big one. Government, industry. Industry requires a lot of water in some cases. The public, the average citizen wants to make sure he's got adequate water supply. And then there's hydrologists, engineers, geophysicists. So if you kind of step up a little bit, don't get too ingrained in actually, the inversion of the 3D conductivity. These are the questions, these are the stakeholders, and this is the level that we should be very cognizant about as we're trying to move forward. I think, here's an image that I think has a lot of substance to it. So what are we looking at here? There's 4 triangles. There's the blue here is geophysics. This is hydrogeology. This is geology. This is geochemistry. The problem that we're trying to address is some kind of a geoscience question here, a geoscience problem. And if we're going to make any progress on that, we actually have to be able to communicate with people, because geophysics clearly sort of role. Inversion can be used in multiple places here. In fact, inversion is used just about every kind of connection that you have. And really interaction is required. So there's communication tools and there's analysis tools that are required to link all of these bodies together in order to really make some impact. And if I kind of look at where I think things have gone over the last few years, it's that the challenges that we're faced as researchers, they just continue to get tougher. Right? And here's a diagram that I think is maybe instructive. So along this line we've got time. This time 1980, 2000, 220, right, whatever. Any deviation of something away from that line is kind of effort. It's the amount of things that's time that's required. And so here's one. So one is the algorithmic problem. Okay, so whether it's a forward or an inversion of data, it used to be that it didn't really take very long because we were working in one dimension and we didn't have many data. So one could go ahead and do an inversion algorithm for that. But these days, when we've got 100,000 data, different timing channels, or whatever, just the inversion algorithm could be really difficult. Then there's the interpretation part, the geoscience, really solving the geoscience problem itself, is continuing to increase because the problems are getting more difficult. They're getting more involved, and it's just simply taking more time. So it used to be like when I was a kid at university, we could be presented with a geoscience problem, and we could go ahead and write an algorithm that would help solve that geoscience problem and actually get a PhD in that, right? But as time has gone on, it's you identify the science problem, and then trying to figure out, okay, what is the algorithm that needs to be generated to solve that, and then to bring it back and see if there's an impact. You just can't do it. It's simply too big a problem to be done. So what we're seeing now is, I think we're getting to the point in sophistication, if we're really going to make an impact and really solve problems that are relevant, that we have to address this fact that the effort for an individual person is simply too large to do. And so we need somehow to do something in order to kind of define the problem. Okay, because actually that's another issue I mentioned, but sometimes you think you know what the problem is. Then you find an algorithm to solve that. But then you take it back and say, sorry, that's not really the problem. So now you're going to redefine what it is you're really interested in. And you got to kind of go back and forth. So that means that there's a lot of communication that's going to be required between the physicists, the astrologists, and the geologists, and we've got to kind of do that. So we need to figure out how to extract information about the physical properties and then how to integrate that into the geoscience problem. So then also that's the question, okay, who's going to do this? Right? So who are the researchers? Are they in industry? I mean, the one thing about industry is that they at least know problems that they're trying to contend with, and they have data, but often that isn't really practical for them to do particular research or share it. And then there's academia, but again, there's challenges there. But so who are the researchers that are going to do it? And what are the tools? The tools for the cooperation are really out there and need to be further developed, but these are basically open source tools. And this, I think, is the future of where we're going. I think in order to really establish that collaboration, that integration, and to cross those hurdles, we need to communicate with people and we need to share. So we need to share both the software, how to implement it, how to apply. So we need that collaboration. And if we're going to collaborate with other groups, then we need to make sure that everything is properly structured, ordered, and organized. And so we need shared repositories, version control, automated testing, documentation, peer review of code, issue tracking, attribution for contributors, licensing, stuff like that. So these are all parts of that culture that needs to be developed in order to make that collaboration happen. I think the good part, and that's really encouraging, at least to me, is that there's been a number of open source communities that are really already doing this. There's AstroPi, which I'm not sure for here. This is astronomy and geophysics department, whether a lot of people are working in using AstroPi. There's scikit-learn, it's all machine learning that's done in Python, and there's SciPi, which is basic scientific computing. There's communities out there that are already moving along in this direction. And I think from the point of view of geophysics, it's actually important that we kind of move along with that kind of mentality. So there's for electromagnetics, for instance, there has again been some movement forward. There's been various packages that have been developed. EM Pylon, there's JM, GeoSci.xyz Australia, PyGimli, Adiando, Simpeg. I think some people might know some of these. They all differ in their objectives, capabilities, structures, but they're all visions of let's generate something that is modular and that other people can use, and let's get this research accelerated to the point where it's useful. The package that we've been most involved with is Simpeg. So it was developed by a large group of people at UBC and other universities, but prime contributors, that is Sagi is one, Betsy Hagley, Rowan Hoffman. It's an open source framework for forward modeling and inversion of geophysics data. So simulation and parameter estimation for geophysics. So it's open source. It's written in Python. There's a number of things that it treats both gravity and magnetic. A lot of the magnetic conversions that I showed you today, those are all available as open source codes in Simpeg. And then there's some DCIP work, and then there's frequency and time domain. So there's code out there that exists. A lot of things that we've developed, I've shown here. So as I said, all written in Python, and with respect to electromagnetics, you can handle these Maxwell's equations that I was talking about. Uses different kinds of meshes, tensor, octree, curvilinear, cylindrical meshes, and with it, it's sort of easy to visualize the fields, fluxes, and charges. Here's a snapshot of something in which you've got a transmitter, conductive plate. Just get to see how the currents are flowing and to understand the physics of what's going on. So all of the Simpeg is available through our hierarchical inroad into the open source, and that is GeoSci.xyz. So if you sign on GeoSci.xyz, then you'll see Simpeg. Actually, you can click on that. There's other things too. There's EM, which actually formed the basis material for the disk. Sagi and Lindsay and I went around the world with the electromagnetic course for disk for UBC. This one, I think, is something that might be of interest. It is of interest to many people. It's called GPG. It's Geophysics for the Practicing Geoscientists. And every university, there's certainly got a geology department. Every university wants to have at least one course in geophysics where the geologists and engineers kind of have some idea about. So the GPG is something that we use for our course. At UBC. And there's a number of other people that are using that material. I would encourage anybody who's teaching non-geophysicists or even first-year geophysicists about geophysics to look at that, but use whatever is available, but even more so, kind of get into that mentality of contributing. There's one thing about open source. A lot of people view open source like, well, that's open, I'm just going to grab this and run with it. But there is, if this community is going to go forward, an obligation on people's part that if I give, I also give, right? So we're a family, we're a team, we need to kind of reciprocate in that manner. And so with all of these things, kind of that feeling of first you get, because that's the easiest thing. But then eventually you've got something like, oh, I could add this, or I could fix up this, right? Or here's bigger that, yeah, that's okay, but I've got a better one. Even starting small, but just kind of getting into that mentality of adding something. And the one thing about the way it's set up is that attribution is there. So if you add anything, put a comment in, it's going to be recorded on GitHub. So that's it. I wanted to thank everybody for coming. We've got some open source resources, and here's the subhead team. That's Sagi, there's Lindsay, Rowan, and then yeah, there's Dom and Tigo, and then the rest of the group. So thank you very much. Around 6 o'clock, not too bad. So that was unexpected day for me. Yeah. Oh, yeah, so I don't know, 8 or 2.